Hi everyone, this will be a video for solving radical equations. Most specifically, you'll see square root equations, but this will also work for any root that you have that you need to solve for. So here's our steps for how to solve a radical equation. The first step is always to isolate the radical on one side. So you don't want to see maybe something being multiplied to it or added or subtracted. You want just the radical on one side. Once you have that, you're going to raise both sides to a power equivalent to the index. So for instance, if it's a square root, its index is 2, cube root, index is 3. You get the idea there. The third step is to solve the resulting equation. So occasionally you do end up with a secondary radical. So you might have a radical still present. That's fine. You can repeat step 2 as many times as you need, where you isolate that radical again, square both sides, or whatever the index was, get the radicals gone. Once you solve, you do need to check your solutions. So not all solutions you find will work. When you plug them back into your original, if it works, that's great, that's a solution. If it doesn't work, and that's what this note down here is saying, if it doesn't work, then that's what's called an extraneous solution. It's kind of, think of it like the word extra. It's extraneous, it doesn't really work for us, but it's something that we found. So here you can see I have a couple different examples here. We're just going to go through them. These are nice, simple equations. They usually don't take up too much space or time, but we do want to make sure that we're focusing, making sure all our small little algebraic steps are correct. So the first thing I'm going to be doing is to make sure that I'm isolating my variable. Oops, jumped ahead of the game there. I'm going to be subtracting 2 from both sides. When I do that, I end up with the square root of x plus 1 equals negative 6. So I need to eliminate my square root. So to do that, what I'm going to do is just square both sides. And so now I'm left with x plus 1 equals 36. Okay, solve whatever you need to do from here on out. So this specific problem, we subtract 1, and we get x equal 35. Okay, so this feels great, but we do still need to check it. So we're going to check. Okay, and when we plug it in, we get the square root of 35 plus 1 plus 2 equals negative 4. Okay, and that means that we're taking the square root of 36 plus 2 equals negative 4. And that's telling us that 6 plus 2 equals negative 4. And I don't know about you guys, but in my book, 8 does not equal negative 4. So we actually have, here's our first one, it's an extraneous solution. So this is going to be extraneous. There we go, fit it in there. So let's try the next one. So again, we need to isolate the radical. You can treat it kind of like an x or just any sort of variable. So the first thing we would do is we would add 9 to both sides. When I do that, I have 3 square roots of 2x minus 1, and that's going to equal a 6. Alright, so now we need to get this radical by itself. So it's multiplied by 3, so we're going to divide by 3. And I end up with the square root of 2x minus 1 equals 2. And here we go. So that's kind of like our first step. That took a little bit longer. But you can see now I have my radical by itself. So we need to get rid of that radical. So to do that, we're going to raise both sides to the power of 2 because that was the power of our index. And we'll simplify. Okay, so our radical gets canceled. We have 2x minus 1 equals 4. And we're just going to solve from here. So when we add 1, we get 2x equal, whoops, let me zoom that. 2x is going to equal 5. There we go. And divide by 2. So we get x equal 5 halves. Okay. So just like our last problem, even though we have an answer that seems like it works, we do still need to check it out. So when we check, we're going to plug it back in, and hopefully it works out to be a true statement. So we have 3 times the square root of 2 times 5 halves minus 1. That's all under our square root. We have a minus 9 equals negative 3. Alright, so we can work from the inside out. Really our radical here is our grouping symbol. So we have the square root of 5 minus 1 Still have everything else going on here. I'm just working little bits at a time. So this is 3 times the square root of 4 minus 9. Oops, equals negative 3. So it's really 3 times 2 minus 9 equals negative 3. It's telling us that this is 6 minus 9 equals negative 3. And negative 3 equals negative 3. This is good for us. This means that 5 over 2 is our solution. Okay, and for one final example, this one's a little bit more challenging. You can see that right now this problem actually has a binomial on one side compared to maybe just a value like on the last 2 examples. So when you're working on this, it's pretty much the same exact steps. This one's actually ready for us, ready to get going, because it does have the radical by itself. We have the radical of 5 minus x equals x plus 1. So we would follow the same idea of trying to eliminate this radical by squaring. That means we're going to square both sides. When we do that, the radical cancels. And really, essentially what we have on this side now is x plus 1 times x plus 1. So a big issue, and I'm going to write something on the screen that's wrong. So this is wrong. So just get ready for this. Okay? So many times I see something like this where it's x plus 1 squared, and I get told that it equals x squared plus 1 squared, which would be 1. This is wrong. Okay? We cannot do that with exponents in parentheses. That can only work if it's just one term on the inside of the parentheses. We have 2. We have a binomial. You need to FOIL this. Most common mistakes with these problems come in not foiling this. So what I have over here in red is wrong. This is not true. This is not nice. Nobody likes it. We want to make sure that we do the correct method here, and that's foiling. So back to the problem at hand. So we have 5 minus x equals, and then we'll FOIL this. We get x squared plus 2x plus 1. Skipped a few steps there, but first outer inner last, and you have your foiling. Now we need to solve this. So since this is a quadratic now, we need everything on one side. So we're going to add x. I'm going to put it underneath of its like term. We're also going to subtract 5, also putting that underneath of its like term. So I end up with 0 equals x squared plus 3x minus 4. And this is a quadratic, so earlier this year we practiced factoring techniques, so we need them right now. When you have a quadratic and it equals 0, we're trying to solve. If we can factor this, we can set both factors equal to 0. So I'm going to try to think of any values that will multiply to negative 4 and combine to 3. And what works for me in my head and on paper would be x plus 4, x minus 1. Because 4 and negative 1 multiply to equal negative 4, which is our C, and combine to equal 3, which is our B. So we set both of these equal to 0. So we have 2 problems now. We have 0 to equal x plus 4, and we also have 0 to equal x minus 1. So negative 4 equals x, and 1 equals x. Okay, again, just like every other problem, we are not finished here. We need to check our work. So let's see, we have negative 4 and we have 1. So our problem here was the square root. We have the square root of 5 minus x equals x plus 1. Let's just double check. Square root of 5 minus x equals x plus 1. So we're going to check out these numbers here. So first we're going to check when x equals negative 4. So we're going to plug negative 4 in. We have 5 minus negative 4 equals negative 4 plus 1. This is telling me the square root of 9 equals negative 4 plus 1, which is telling me 3 should equal negative 3. In my book, not the same, so this is an extraneous solution. So negative 4 is extraneous. Let's check our value x equals 1. So when I have the square root of 5 minus 1 equals 1 plus 1, square root of 4 equals 2, and 2 equals 2. This is great. So that means that x equals 1 is our solution. Okay, so even though we did find two values, sometimes both of them don't end up working. So sometimes both might be extraneous, but one of ours did end up being a solution.